Every large-scale web application eventually hits a physical bottleneck. When millions of global users request content simultaneously, a single centralized origin server buckles under the volume of incoming traffic. The physical distance between that server and the user dictates the baseline latency of the entire system. A content delivery network addresses this by caching assets at edge points of presence, or POPs, located in close proximity to the clients. Modern CDNs operate through two distinct layers. The data plane processes client requests, terminates TLS handshakes, and manages caching paths. The control plane handles configuration distribution, security policy enforcement, and global purge requests. To build a high-performance global CDN from scratch, we must solve three specific engineering challenges. First, structural topology. Second, global request routing. And third, cache consistency. While local caching is a standard mechanical task, the true complexity of the edge involves routing users to a mathematically optimal node while keeping distributed state consistent across thousands of servers. The fundamental physical building block of the network is the point of presence. These are micro data centers deployed in diverse geographic regions to reduce the physical span of a request. High-performance POPs utilize a stateless design to maximize scalability. Removing state from individual edge devices simplifies networking topology. Incoming traffic hits the POP's Layer 3 switches directly. This replaces traditional state-heavy load balancers. These switches use equal-cost multipath routing, ECMP, to distribute traffic across local Layer 7 PASH servers, processing packets across multiple paths based purely on IP addresses and hardware. Bypassing stateful load balancers in favor of pure Layer 3 ECMP routing reduces bandwidth costs and eliminates single points of failure. This allows the POP to handle massive traffic spikes natively at the network level. Before a POP can serve content, the routing layer must direct the user to the most optimal edge location. The legacy method, DNS unicast, assigns each POP a unique IP. A global server load balancing system resolves the hostname, returning the IP. DNS unicast routes traffic based on the DNS resolver's location, misrouting users to distant POPs. Anycast fixes this. Multiple global POPs advertise the identical IP address using the Border Gateway Protocol. Routers use natural network flow to forward packets along the shortest topological path. Anycast provides built-in network failover. If a POP goes offline, its BGP session is withdrawn, naturally redirecting traffic to the next closest location. This architecture also absorbs DDoS attacks by spreading hostile traffic across the entire global network. By routing based on true network topology, Anycast ensures every packet travels the shortest possible distance to the edge. With the data plane optimized, the challenge shifts to the control plane. Maintaining global cache consistency requires solving one of the most difficult problems in distributed systems, invalidation. Relying on time to live, or TTL, expiration is insufficient for urgent updates. URL-based purging creates a severe bottleneck. When updates affect hundreds of pages, purging each individually by URL is too slow to maintain consistency. Surrogate key purging scales massively. The origin issues a single invalidation request to the control plane, targeting a metadata tag that groups related assets. The control plane propagates this command globally, and edge nodes remove all matching assets in roughly 150 milliseconds. This transforms cache invalidation from a slow, iterative process into a parallelized global state refresh. Modern edge nodes function as compute environments, executing serverless code directly at the network's fringe via runtimes like V8 isolates or WebAssembly. These edge environments maintain their own internal fetch caches, creating a dual-layer caching challenge. If a purge only clears the outer cache, subsequent requests trigger the edge function. If the function's internal cache holds stale data, it returns old content, recontaminating the outer cache. To prevent this, the pipeline coordinates invalidations across both layers simultaneously, using programmatic purge APIs. In an environment where the edge executes dynamic compute, cache consistency is a coordinated multi-runtime requirement. We can now visualize the complete request lifecycle of a high-performance edge architecture. BGP Anycast steers the client to the nearest POP. Inside that POP, ECMP load balances the request down to the optimal Layer 7 server host. On the control plane, origin updates trigger surrogate key purges that synchronize across outer caches and internal worker states in under 200 milliseconds. Large-scale enterprise architectures often use multiple CDNs to ensure high availability and route traffic based on regional performance. A centralized multi-CDN controller keeps these networks synchronized. It translates invalidation intent across providers, mapping tags to URL lists for platforms that lack native surrogate key support. Reliable content delivery at a global scale is built on the rigorous application of stateless topology, natural network routing, and sub-second global state synchronization.